In this section, we want to introduce a new method for solving systems of equations, whether we have 2 equations, 3 equations, or even more equations, as we'll see, which is using neither the elimination method nor the substitution method. Instead, what we're going to use are something called matrices. A matrix is just a set of numbers arranged in rows and columns, but are the specific matrices that we construct for these applications will be converting a system of equations into what we refer to as an augmented matrix. So looking at example 1, we have equations which we can refer to as equations 1 and 2. What we want to do is convert these 2 equations into that augmented matrix form. So what we'll do is just take the coefficients for each equation. So in equation 1, we have the coefficient for x is +1, the coefficient for y is -7, and then we have a constant on the right-hand side, which is 5. We'll apply the same idea to equation 2 to get 5, 3, and 2. What we've done here is constructed a matrix, so a set of numbers organized in rows and columns. To create an augmented matrix, though, what we'll do is add a vertical line, which takes the place of essentially the equal signs that we had in our equations, separating all of the variable coefficients on one side from the constants on the right-hand side of those equal signs. Let's apply that same idea in example 2. Again, we have equations 1 and 2. To start off, though, we need to make a change, or a couple of changes. In example 1, we had our variable terms all on the left-hand side, our constant terms on the right-hand side. We need these equations to be expressed the same way. So to start off, what we'll do is add our constants to the right-hand side, which will give us x minus 7y is equal to 7. And for equation 2, we'll get 5x plus 3y is equal to -2. Now we can turn this into our augmented matrix by, again, taking the coefficients for each row and then adding that vertical line in place of where the equal sign would exist in our equations, separating, again, the variable terms on the left-hand side with the constant terms on the right-hand side. In example 3, we now have a system of 3 equations, but this method still works. We can convert this system of 3 equations into an augmented matrix after we make one small change, or at least notice one small change that needs to happen in equation 2. Equation 2 starts off with 5x plus 5y, but then what we're missing is a z term. So we either want to rewrite that or just keep in mind that we'll need that placeholder 0 when we transfer things over to this augmented matrix form. So translating equation 1 over, we'll have 1, -1, 1, and then 12. For equation 2, we'll have 5, 5, and then in place of our z variable, we'll drop in a 0. And then we'll have a 4 as that constant term on the other side. And then equation 3, we can translate over as well. One way in which matrices become very helpful is that they can be used for larger and larger systems. So in this case, what we have is a system of 1, 2, 3, 4, 5 equations. Solving this using the methods of elimination and substitution that we've seen previously would become a very cumbersome problem. But in this case, we can translate this all over. putting in placeholder zeros for those missing W terms in equations 2 and 3. To complete that matrix. So the techniques that we introduce in this section would be able to solve a system of 2 equations, 3 equations, or even in this case a system of 5 or more equations. The process would, of course, still take longer to complete, but wouldn't be as cumbersome as expanding some of the methods that we've used before to these larger and larger systems. We also want to make sure that we can take an augmented matrix and convert that back into a system of equations, which is something that we'll do at the end of every problem to generate our solutions. In this case, we want to keep in mind that all of the numbers in our first column were the coefficients for our x variables. All of the numbers in our second column were our coefficients for the y variables, and then our third column related to those coefficients for our z variables. So to translate this back into a system of equations, this would become 1x minus 4y plus 4z. That vertical bar again represents that equal sign in each of our equations, so that would be set equal to 2. Our second equation would become 6x minus 5y plus 6z is equal to 4. And then our third equation would be minus 8x plus 5y minus 5z is equal to 4. So this idea of being able to translate back and forth between systems of equations and augmented matrices will help us take our system of equations and set them up to be solved using our matrix operations. And then in the end, we'll translate back to a system of equations to come up with our order triples.